Okay, I have the time at 11, so we'll go ahead and get started. We're going to continue our discussion of alkene addition reactions. So we got sort of disconnected last session. So what we're going to pick up on is another example of the hydration of an alkene to give an alcohol. And this is a good example of what is known as Markovnikov's rule. And so it's stated here two ways. So when we have an alkene, again, the alkene is the nucleophile, and we're treating it with some electrophile. So this is going to be the addition of water across that alkene. Markovnikov's rule states the carbon bearing the most hydrogens will be protonated. So that's an example of where the electrophile is a proton. But in general, statement number 2, the addition will occur to generate the most stable carbocation. So statement 1 is really pertaining to acids. Statement 2 is pertaining to electrophiles in general. So again, Markovnikov's rule is gives us guidance on how we add the electrophile to the alkene, because remember, we have a regiochemical issue where the electrophile could add here or there, and so this gives us guidance. So knowing Markovnikov's rule, let me write, I'm going to write A and B next to those two carbons of the alkene. So under these conditions, we're treating with water and catalytic sulfuric acid. So that generates hydronium ion as the electrophile. So given Markovnikov's rule, which carbon, B or A, will be protonated? So feel free to type your answers in chat. So we have 3 students typing A. So again, A is basically agreeing with this statement. So we look at A and B. A has 2 hydrogens, so 1, 2. B has 1. So A has the most hydrogens. So when that's protonated, what is the classification of the resulting carbocation? So we're looking for primary, secondary, or tertiary. So we're generating a secondary carbocation. So just to prove to ourselves that Markovnikov's rule is correct, if we protonated B as an alternative pathway, what is the classification of the carbocation that is generated? So I was looking down, assuming these answers just came in, primary, primary. So yeah, if we protonate B, we generate a primary carbocation. And again, we're trying to generate the most stable carbocation. So we're gonna protonate A to give the primary or the secondary carbocation. The alternative pathway is not going to be favored. So now we get to here and we have to ask ourselves a question. So here's our alpha carbon, here's beta, and here's beta prime. The question is, can this carbocation rearrange to form something more stable? And we answer that by evaluating the beta carbons. Beta is not equal to beta prime because we have a methyl group, 1, 2, 3 hydrogens. We have this now tertiary beta prime. We have a hydrogen here, 1, 2, 3 carbons. So what we also have to recognize is the difference between a hydride shift and then an alkyl shift. So we definitely don't want to have a hydride move over because that's going to put a plus charge there, and that would be the same route as if we just protonated B to begin with. So we don't want to do anything with beta. So now we have the choice at beta prime. We can either have this hydrogen move over as hydride. That would generate a tertiary carbocation. But the issue is it's a tertiary carbocation that's going to experience quite a bit of angle strain because it's present in a cyclobutane. The alternative choice is if we actually have a carbon-carbon bond migrate over to expand the ring to a 5-membered ring. So the bond that I'm drawing now is the bond that has migrated. And I'm sort of keeping the drawing the same just so you can see how it's migrated. So the plus charge goes from here to there. And so it is a degenerate carbocation in the sense that the secondary, it's still secondary, but what we're doing in the process is we are relieving the ring strain. Remember that this internal angle here is 90, and then as we go to 5, we're expanding that, so it's better able to accommodate the plus charge. So Hannah, I'll get to your question in a second. So at this point, we're going to have water trap. And then we finish off by doing a proton transfer. To end up with our alcohol. So the issue So the issue with having this hydride migrate over is that you're putting the plus charge on a carbon that's pretty strained in terms of a 4-membered ring. So again, the 4-membered ring is strained because the bond angle is 90 and it wants to be 109.5 for an sp3 hybridized carbon. So we rationalize that not happening by there being, even though it's tertiary, you're still experiencing that strain in the four-membered ring. So we're going to use Markovnikov's rule in a very general sense moving forward. Basically, we're going to sort of put these two statements together and think of things in terms of the electrophile. No matter what the nature of the electrophile is, it will always add to the most substituted carbon so that you get the most stable carbocation. So we're going to move on to this reaction now, which is Alkene Hydrohalogenation. So just as the name implies, we're adding a hydrogen and a halogen. So we have an example here. Consider 1, 2, 3. We have an alkene propene. We have HBr, that's an acid. And now I'm telling you that the major product is 1, 2 bromopropane and not 1 bromopropane. So what is the first thing we should do in terms of showing the mechanism? So that's what we're looking at right now. So I've sort of given you the clue. These are the elements HBr, and we've showing them add across that alkene. So we're adding it in a regioselective manner. So if I put in this H here, now you can see those elements of HBr. So we have delta minus, delta plus. Here's your electrophile. Here's your nucleophile, the pi bond. Now, as we see, the terminal carbon has 1, 2. So this carbon is going to get protonated. And in doing so, we generate a secondary carbocation. So we push our arrows. Again, this is an example of a polar reaction mechanism. And remember what we meant by polar. That's the movement of 2 electrons. And as a review down here, where it says recall, we'll show radical, because that gives a different product distribution with the same starting material. So we've added our hydrogen. Now we're going to add the Br minus. Again, notice plus, minus, we're balancing out the charge. Nucleophile, electrophile. So at this point, this is a fast step. We're going right to that final product. And again, the reason we would not protonate here, that generates a primary carbocation. So the major product is 2 bromopropane. So what I'm showing you down here where it says recall is that under these conditions that are listed, so you have HBr, now you're running this reaction in the presence of tert butyl peroxide and heat. Now the product distribution flips. The major product is the 1-bromopropane. So even though this is not going to be so much of an issue for you guys because you are not, I repeat, you are not, if you have not read the syllabus, you are not taking a cumulative final exam for this semester. Your Module 5 exam is next Monday, and then you are done with this course. The reason I mention that is because we've gone through the radical module already, and you don't really have to know the context of HBr tert butyl peroxide. If we were taking a normal final exam, you'd have to know the context of these different reactions. But essentially for Module 5, you're only dealing with the polar mechanisms. So what happens in this case? These conditions generate a bromine radical. The radical then adds to the alkene to give the more stabilized radical. So let me just, as a review, show you what happens here so you can understand why these two are different. So tert butyl peroxide, in the presence of heat, forms two of those radicals. That generates the inert alcohol, tert butanol, plus now your bromine radical. The bromine radical now has a choice. Of which carbon it can add to. It adds to carbon A because that generates a secondary radical. So I'm going to take a beaten path here. So secondary radical. That then reacts with HBr to give you the primary alkyl bromide. So the two methods are complementary. And what you have to recognize is the effect of this peroxide on the regiochemical addition to the alkene. So again, that's just a review. You will not see that on your Module 5 exam. Any questions before we move on? You're not going to see the bottom conditions on the final Module 5 exam. So as I said, 255 at the end of the semester and 256, we're really getting into applying everything that we've learned in terms of new reactions, functional group transformations, and synthesis. So we're learning a lot of alkene reactions. This next one is alkene halogenation. Here's the general alkene. There's your pi bond, nucleophile, a molecular halogen, electrophile, either chlorine or bromine. So this reaction under these conditions forms a vicinal dihalide. So what does vicinal mean? They're in a 1-2 relationship. So that's what we mean by vicinal is 1-2. And that's just relatively speaking. So if this was 1, that would be 2. That doesn't deal with the IUPAC numbering scheme of the molecule. It's just a relative relationship. So I'm going to show you an example here. using cyclopentene. So 1, 2, 3, 4, 5. Cyclopentene. We're looking with perspective, edge on to the alkene. We're treating this with bromine and dichloromethane. So this is important because we're going to see conditions in a couple slides where the nature of the solvent changes. Dichloromethane does not participate in the fact that it's just there to solubilize everything, and it does not end up in the final product. We're only adding bromine across the alkene. So here, bromine is the electrophile. Again, your alkene is the nucleophile. Now there is remember when I mentioned about facial selectivity in top versus bottom? So the bromine adds to the alkene in a very select fashion. So if you think of the van der Waals radii of bromine, bromine's pretty big. So molecular bromine, the interatomic distance is pretty big. So the bromine is not adding to the same face at the same time. So what ends up happening is that the bromine approaches the alkene in the following fashion. So it's more like orthogonal rather than parallel. So the bromines do not add at the same time, they add separately. So I'm going to show you the arrows of how this happens, and there's going to be something a little strange about the concertedness of this. Concerted meaning simultaneous, like time-wise. So we know that there's induced dipole interactions. So one of these bromines can be delta minus, one can be delta plus. This is just the nature of the electrons moving. When that little bit of plus charge shows up, the alkene can come down and attack. We can then break this bond. What has been found out that happens additionally during this step is a lone pair from bromine also comes up. And so you end up with an intermediate species that is called a Bromonium Ion, where the plus charge resides on the bromine rather than the carbon. So what does that look like? So the reason I want to put the stereochemistry in here of these hydrogens in the ring is for the following reason. So again, we're sort of looking edge on. Now if we count 1, 2, 3, 1, 2, 3, we end up with a 3-membered ring. So the plus charge is on the bromine. Now what I'm going to do is just fill in the rest of the ring. And so now you can think of the bottom face of the alkene as being blocked by bromine. So the bromide, IDE, bromide anion that left is going to then approach from the other face, the top face, and attack. So it's going to attack in an anti or 180 degree fashion. So say it comes here, So I've put the bromines in. Now you can see, if you were to look down a Newman projection of that, you would see that they're anti. Let me go ahead and put in the hydrogens now. So this is an anti-addition. The bromines end up being trans. So a question you should ask yourself is, if the bromine attacks this carbon, why can't it attack that carbon? And it can. So there's the relationship that's trans. Then we put in the rest of the ring. So given that information, what is the relationship between those two products? Can you be a little bit more specific about what type of stereoisomers they are? So these are enantiomers. So if they're enantiomers, we're starting with an alkene that is achiral, the bromine is achiral, the solvent is achiral, we're forming enantiomers. What ratio do we form those enantiomers in? So we're forming both of these. Again, an enantiomer is a mirror image stereoisomer. What's the ratio that we form these in? So we form them into 1-to-1 ratio. And then if we were to take a sample of that and put it in a polarimeter, what would be the optical rotation of that sample that's 1-to-1 of each enantiomer? So the specific rotation is going to be 0, because whatever direction this rotates the plane polarized light, this is going to rotate it the opposite direction. The fact that they're 1-to-1, that's how you get 0. So just as a little bit of practice, what is the R or S designation of this stereogenic carbon? So this one's R. So because these are enantiomers, if this is R, then this, so this is the mirror image carbon, this has to be S. So then what about this? This one right here, the CIP, Kahn-Ingold Prelog, is this R or S? So we have 1, 4, 2, 3. Does everyone agree with that? That's our lowest priority group. If we're doing 1, 2, 3, because it depends on how you're looking at the orientation of this. I would agree and say that this is R and not S. So you have the RR and the SS. And again, you can tell by that designation, looking at these, that those are enantiomers. Blakely, you have to look at, you have to put the lowest priority group away from you. Let me notice this trans orientation. Let me just as a review, so as a review, consider those two structures. What's the relationship between those two structures? Upside down is not a relationship. So Taka has the right answer. They're the same. What is another another definition for this type of molecule? Put another way, what is the relationship between these two and this compound? So again, this, they're all stereoisomers. We said these are enantiomers. What is the relationship between these two and this? Again, these are the same thing. So this cannot be an enantiomer of this. So this is a diastereomer of these two. So what is a special name for this? Because remember that for every stereogenic carbon, you have either R or S. So therefore, if you have two stereogenic carbons, you have 2 to the 2, 4, 1, 2, 3, 4, but these are the same, so you only have 3. So what is another word for this compound? Do you remember? It's a compound that has stereogenic carbons, but now an internal mirror plane, so it's a meso compound. So the fact that this is meso is why it reduces the potential for 4 down to 3. So that's why you don't end up with the maximum number of stereogenic stereoisomers. Now what I want you to do on this slide before I write anything down is to consider the mechanism you just saw for bromine adding to the alkene. But now we have two alkene geometrical isomers. So here we have the E, or the trans 2-butene, the Z, or the cis 2-butene. So considering the mechanism that you just saw, that bromine does a trans addition, how many products can you get for this and for this? So take a minute, think about that. Again, you're considering the addition of bromine to each of these alkenes. What are the possible products? So one sort of way to solve these that's fairly straightforward. This does say olefin, yes. So one way to solve these is you know that the bromine is doing an anti-addition. So there's the anti-relationship. Now if you plug in your substituents, what is the relationship between those two compounds? Olefin is another word for alkene. So are these compounds enantiomers? Who thinks they're enantiomers? So this is actually a meso compound because when you rotate about that sigma bond, so I'm rotating about the sigma bond. So this actually ends up being a meso compound. What about for the Z2-butene? Does the same thing happen? If not, what are the products? So I would say go ahead and add in. There's your trans relationship. We've then added in our substituents. Do these end up being meso? So these are not meso compounds, so these actually end up being enantiomers of one another. They are not meso because this H is not mirrored by the methyl. This methyl is not mirrored by this H. So you might quite possibly see this word used in your reading here. Called stereospecific. Stereospecific relates to looking at the nature of the product that is formed and being able to infer what, say, the starting geometry of the alkene was based on how the mechanism proceeds. So the same conditions, different alkene geometry. This results in a meso compound. This results in a set of enantiomers. Any questions before we move on? So now we're going to look at another set of conditions that uses molecular halogen, but now the solvent that we're using is either water or an alcohol. So now we have a protic solvent, whereas before we were using dichloromethane, which is not protic. So we have a nucleophilic oxygen, and these actually participate in the fact that you end up with incorporation of the halogen and either an alcohol or an ether, depending on whether you start with water or an alcohol. And so these are called halohydrins. So we're going to consider the reaction shown with cyclohexene. Now what I've done, and I've put my eyeball here and I'm looking at the alkene this way. So edge on, so this perspective here. And I'm doing it that way just to show you how the addition occurs, because we know that the bromine is going to form the bromonium ion, and then because there's so much more solvent than there is bromide, this ends up being the nucleophile in the second step. So what is our first thing that we're going to do? Here's the bromine. The alkene attacks, we cleave that bond. The bromide lone pair then forms the bromonium. So that's a three-membered ring. Let's just go ahead and draw that first. Then we can put in our stereo chemistry with perspective. Those are the hydrogens. Here is the rest of the six-membered ring with some perspective. So we have 1, 2, 3, 4, 5, 6 carbons. So again, because there's so much more solvent in a reaction than the bromide, the solvent is actually going to be the nucleophile at this point. And when that happens, it's approaching from the opposite face in an anti-addition. So let me draw that anti-relationship first. And I'm going to put in the rest of the ring now. So there's the rest of our six-membered ring. So as a consequence of this adding anti, you get this trans-diaxial relationship. We're going to do a ring flip and a proton transfer, because we remember that diequatorial is more stable. So I'm not showing the proton transfer, but essentially what's happening is the bromide or the water is removing that H to give you the neutral species. So that's a review of cyclohexane conformational analysis, in the fact that the diequatorial is more stable because you're relieving the 1,3 diaxial interactions. I didn't know what you mean by triple bonded to the alkene. So when you have these ring systems and you do an anti-addition, they're always going to add, so you get the trans-diaxial, and then it will most likely do a ring flip to give you the more stabilized conformation. So to convert this into the flat cyclohexane, we have our bromine up, we have our alcohol down, so that's how we would represent it that way. Does anyone know what this means? What does it mean? This means that this and this are equivalent. This does not mean it's a triple bond. So one thing I just want to show you real quick is you can take these things these bromohydrins, treat them with sodium hydride, which is a base. THF is your solvent. That's the structure of THF. So if sodium hydride is a base, this is an acid. If we do a proton transfer, we generate this, which is an alkoxide. So that's an intermediate that can then do a displacement to end up with a three-membered ring, ether, which is called an epoxide. So overall, that's a two-step process to take an alkene to a halohydrin and then take that to an epoxide. So on this next slide, I call this putting it all together, and I use this term retrosynthesis, which is the organic synthesis concept of reverse engineering. So if you had to supply the reaction conditions or steps to take cyclopentane into this cyclopentane oxide or this epoxide, what steps would you propose to do this? So you've learned all of the chemical reactions on how to transform this into that. But what is sort of difficult is sequencing them in the proper order. And that's what organic chemists do for a living. You take things that are hydrocarbons, so non-polar, you run a series of reactions and you put functional groups into them so they're polarized. Why do I have this word up there, and how does it help us? So at this point in the semester, even though we only have 2 remaining lectures, we're going to talk about this in 256, so quite a bit. You're really, instead of thinking forward, because that can be sort of difficult in how you sequence all the reactions you know, you look at the final product and then you think backwards, and that's called retrosynthesis. So the associations that you're making are just sort of in reverse. So the way I like to teach this is, again, just simply write down what is the functional group. It's an epoxide. This arrow that you see there is called the retrosynthetic arrow, and it's just a thought arrow. how can we simplify that final thing into something we do know? So it's not a reaction so much, it's just a design or a blueprint. So we know that we can make an epoxide from a bromohydrin. You just saw that. So in the forward direction, that would be sodium hydride and THF. Bromohydrin, we know that that comes from an alkene. So our retrosynthetic arrow, we know that we can add Br and OH across the alkene using bromine water. So that's the forward direction. How do we synthesize alkenes? We can synthesize those through elimination of an alkyl halide. So sodium ethoxide in ethanol. Again, that was our E2 reaction. So alkenes come from alkyl halides through elimination. How do we get to alkyl halides? Well, we can get to alkyl halides from the alkane. Using bromine and light or heat. So that's a radical CH substitution. So we've proposed 1, 2, 3, a 4-step synthesis on how to take cyclopentane to this cyclopentane oxide through CH functionalization. So we saw that in chapter 10. Then chapter 7 and 8, we saw elimination to the alkene. Now we're seeing in chapter 7 or chapter 8, addition of bromine water, and then another substitution reaction where the base deprotonates. We have nucleophile, electrophile in the same molecule to substitute out the bromide. So I would say probably thinking in the forward direction and sequencing this is probably pretty challenging. So that's why we use retrosynthesis to identify functional group transformations that we know. And then we can sequence them in the forward direction. So we're about out of time, but what we'll do on Wednesday is look at dihydroxylation of alkenes to get 1,2-diols. Then we'll look at oxidative cleavage, where the alkene is transformed into carbonyls, and then we'll start our chemistry of alkynes. Friday, we'll finish up the chemistry of alkynes. Again, you can just view an alkyne as 2 double bonds. That's how we can simplify our life, because you've seen alkene addition reactions. The alkynes are going to be very similar. And then Monday you have your homework sets are due, and you have your Module 5 exam. And then once you're done with that, you're completely done with everything. So you don't have to do anything past Thanksgiving break.